Okay, please have a seat and make yourself comfortable, and don't forget to switch your phone into silent mode because we will start our second session in 3 seconds. 3, 2, 1. Okay, here is it. Dr. Khoa Nguyen, the second part of Lattice-based cryptography. Thank you very much.
Thank you again. Okay, so let's continue with our lectures. Okay, so let me give a short picture about cryptography from SIS. So the average case, worst case to average case reduction says that the problem is, this SS problem is as little as high as geometric lattice problems. And what we will do now is that we show that cryptography can be built based on top of the harness of the SS problem. Okay, so let me review some known constructions based on SAS. We can build, firstly, we can build one-way functions. You know, one-way function is the very, very basic, the necessary building block for any secure cryptography system. So one-way function says that there are some functions that are easy to evaluate but hard to invert. That is very important because to guarantee the security of our system, we must give some hard text to the adversary, to the attacker, right? So from our side, we have to be able to do it efficiently. But from the attacker's side, it should be hard for them to do this attack. Then we must assume that there's such a function. So it's one-way function. One-way function is connected to the most important open problem in theoretical computer science, the P vs NP problem. Okay, so if one-way functions exist, then P does not equal to NP. Okay, because suppose that you have some inversion of the function, so you can easily verify by just re-evaluate that function. But finding this is hard, so we assume that P does not equal to NP. Okay, so equivalently, if P equal to NP, then there does not exist one-way function, and there does not exist secure cryptography as well. So, as a cryptography researchers, I hope that P does not equal to NP. Otherwise, I will lose my job, right? Okay, so it's very okay. So it's connected to the most. So the common view is that P does not equal to NP, and this is one of the 7 millennium problem by the Clay Institute of Mathematics. So if you can solve it, you will be a millionaire with the $1 million prize from the Clay Institute. It's the most important problem in open problem in theoretical computer science. It may give you a Turing Award as well. So please prove that P does not equal to NP. Okay, so we can also, except for one-way function, which is the most basic primitive, we can also use SAS to construct collision resistant hash functions, commitment schemes. Okay, so in these lectures, I will try to cover one-way functions, collision resistant hash function, and maybe commitment schemes. We can also use SAS to construct identification protocol, zero-knowledge proofs, signatures, and more advanced construction that require some combination of the above, like signature and some privacy preserving constructions like anonymous credential and so on. Okay, so let's start with one-way functions. Okay, so what's my goal here? So my goal here is to construct a one-way function based on the harness of the SS problem. If you read a typical research paper in cryptography, so basically normally the authors do not give such detail like this. In fact, they often assume that the reader have the prior knowledge about this. They don't go to the detail. But I would try to go to the very detail with this easy primitive, so that you have the sense of how security is defined in modern cryptography and how to prove security. Okay, so it may help you to read a research paper in cryptography easier in your future research career. Okay, one-way functions is defined as follows. A function f mapped in domain D to range R is called one-way if it has these following properties. First, it must be easy to. Okay, so we can't easy to evaluate, but how to formally define it? It says that for any x in the domain, it is computationally efficient to compute f of x, which is y, belong to the range. So computationally efficient means that in the theoretical sense, means that there is a polynomial time algorithm that given x give an output on input x, output y. And it means that in implementation, it must be fast. Okay. The second property that makes it one way is that it's hard to invert. So on one way, we can evaluate the function easily. On the other hand, it's hard to get back to the preimage. Okay. So given y, which is equal to fx for some x, okay, must be computationally infeasible to compute some x prime in the domain such that f of x prime equal to y. Okay, so here, infeasible means what? Infeasible, that means computationally infeasible, or just infeasible means that we give the adversary polynomial time and space, and we expect that he's still unable to do this task. So it's very commonly used terminology in cryptography and theoretical computer science and complexity theory. So it is different from impossible. So when we say impossible, it means that we give the adversary unlimited power. All of the power that he can have, unlimited one. Not polynomial, even exponential, he can still he's still unable to do the task, so it's called impossible. So it's very strong. But here we just use the term infeasible. It means that adversary has limited polynomial time and space. Okay. That is what we expect from one-way function. But formally, to prove security of the system, we have to define the primitive rigorously. In fact, as I mentioned at the beginning of the lecture, the work by Gowasser and Mikali was the first one to define what does it mean for a given crypto system to be secure. And that's very important for the development of crypto. If you don't have a rigorous theoretical foundation, you don't work out the definitional framework, then it's very hard to make progress in any field. Okay, so let's formally define what is one-way function. So we know by lambda, the security parameter, say that is if lambda is bigger, then we expect more security in the system. So in practice, we can set lambda to be 80 or 128 or increasing. And let f be the family of functions, small f, mapped in D to R. And, okay, so security for cryptography system are defined in terms of a game between two parties. The first one is called the challenger, and the second one is adversary. So challenger is who? Challenger is the designer. You can think of the designer of the system who set up the system and give it to the attacker, or we call the adversary here, and say that, okay, please attack my system. And adversary is going to attack the system, okay? And we model the security of the system based on a game between the two. Okay, so the game for one-way function is as follows. First, the challenger choose of uniformly random function f from the family, and uniformly random preimage x in the domain. Compute y equal to f of x, and send the description of the function f and y to the adversary. So, in fact, it captures this one. It captures the fact that I take some x, I choose some uniformly random function in the family, I give this one, and I give this one to adversary. Adversary to show that it's not hard to invert, right? Okay, so adversary will output x prime in the domain such that f of x prime equal to the same y here. Okay, so in the game here, we try to model the fact, what does it mean for the adversary to win? Okay, so it wins if it given f and y, it can output x prime, so that f of x prime equal to y. And the security of our system is defined based on the fact that on the probability that the adversary does not win. Okay, so the family of functions is called one way if for any polynomial time adversary A, so the probability that A wins in this game is negligible in the security parameter. So we have a system that we can prove that any adversary within polynomial time cannot win this game at defined with non-negligible probabilities. Then the system, then the function, we can prove that is one way. Okay, so that's the definition. So, okay, is there any question about this? If you read some survey, for example, in Lattice-based crypto, for example, the one by Professor Chris Pickett from Michigan, so I think this part will normally skip, and for beginner, it's very hard to capture the ideas underlying on the construction. So maybe it's time consuming for us, but I would try to follow this approach. We build everything from the very, very basics. We may run out of time for that. Okay. Okay, so let's try to construct a candidate of one-way function from SAS. Why I call it candidate? Because we don't know whether one-way function truly exists, right? Because we don't know the solution for the P and P problem. But there are some, because in crypto we have to believe in something. In this case, we believe that SAS is hard. So, based on this assumption, we can build a one-way function. So let n be the security parameter, so it's related to the lambda in our system. And let q be some modulus enough, like just of order of n square. And let m to be some dimension bigger than n log q plus n, say. So we define a family F, which is the collection of all Fa for on A, for on matrix A in ZQ to the n times m, and it's mapping 0, 1 to the m to ZQ to the n, where x mapped to Fa of x equal to Ax mod q. So it's the same as the one that I wrote on the board. So it's very simple. I guess that we want to show that this function is one way. Okay. Okay, so we have this theorem. If the SS problem with parameter n, m, q, and square root of bit of m, okay, then f is one way. Okay, so now we try to prove this theorem. Okay, so what is the goal security proof in cryptography. So we want to show that this function, in this case, we want to show that this function is one way, and we prove by contraposition. It means that we assume that adversary A can win the game that we define with non-negligible probability. Then we will show that the challenger can use that adversary to solve the SS problem with non-negligible probability. And since we assume that there's no efficient algorithm to solve this one with non-negligible probability, then it means that there doesn't exist such an A, right? So if we can show this statement is true, then our system can be proved one way. In fact, equivalently one way under the harness of SS. Is it clear? If adversary can attack the one-wayness of our system, then we can solve the SS. But SS is hard, then we can deduce that no such adversary exists. Okay. Okay, so now prove this statement. Okay, so in security in cryptography, so okay, so if you look at the game, so there are challenger and adversary interact with each other. Okay, but now we have another entity in the picture. That is the problem. SS problem. Where is it? Okay, so the general strategy for doing this is we have another party here, say the problem oracle. You see, okay, so let me try to so we currently we have an adversary, the challenger of the one-way function, challenger of the one-way function, and the adversary of one-way function. So they interact as specified in the game that we define. Okay, but now we have a problem. Then we have another challenger, but of the SS problem. Okay. And this guy, in fact, he output a random instance of SS problem, and it gives to the challenger of the one-way function. Say, so the challenger of the one-way function, in fact, he played two roles. He also played the role of the adversary of SS. So what happened here is that this challenger of the one-way function first this challenger of SS give me an instance of the problem. I will solve it. Okay, and this guy will give us some instance of the problem, and this guy, the middle guy, will try to use that instance to somehow embed it into the game with the adversary of the one-way function. Try to simulate the game somehow. Try to trick him and let him to help the challenger here to solve this one. Okay, so they interact somehow. This guy try to embed the instance of the problem to the game, and they interact at some point. Because this adversary, what's his promise? He promised to attack the one-wayness of the function, right? So at some point he will attack, and he will output some X prime as defined by the game. And this guy, if he succeeds, he can use the solution given by this one to solve this one, and he can return this one. So basically, maybe you don't see it in a normal crypto paper, but in fact you can view the whole picture like this. There is a guy challenger in the definition, but in fact he must guess the problem somewhere else, so that he can solve it eventually. So this guy succeeds with some probability epsilon, for example, and this guy then he succeeds with some problem, some function of the epsilon prime. then what we deduce, so this, if this guy success good, if epsilon here is non-negligible, and if we can argue that this epsilon prime is also non-negligible, then in fact we are done, right? Because our assumption is that no one can solve SAS with a non-negligible probability. Okay. Is it clear? Okay, so maybe you think it's too complicated even for one-way function. So normally we just let it go. Okay, so it's one-way function in this way. But if you think about this picture, so I guarantee that it will be much easier for you to read research or survey paper in Lattice-based crypto in particular and public key crypto in general, modern crypto. Okay. Okay, so our proof goes as follows. First, the challenger here is the challenger of the one-way function. He receives a challenge instance A from the challenger of SAS, right? Because you know what is the definition of SAS? It is given matrix A, uniformly random, actify some x star, such that x star is non-zero, and A times x star equal to 0 mod q and x. Okay, so I think there's a typo here. It should be x star. The norm of x star is s mod square root of m. Okay, so if the challenger of the one-way function can achieve his goal, then he can solve SAS, right? And now his task is to use this instant A somehow to simulate his game, his own game on the right-hand side with the adversary of the one-way function. Try to simulate, try to cheat him, try to let him help to give some help in solving this problem. Okay, so now what the challenger will do, choose a uniformly random x in the domain and compute y equal to a times x mod q and send a times y to the adversary. Send this pair, the matrix A, would describe the one-way function fa and the image y to the adversary. Okay, here my question is, why won't adversary A abort the game? Okay, so something quite subtle here is that this guy, because we have a definition of one-wayness, right? So so the rule is that adversary A promised to break the one-way function. But this challenger also have to promise that he follow the game. But in fact here, maybe he's not follow the game, but he try to simulate, try to proceed with the game in a way that is indistinguishable for the adversary. In fact, he's doing some cheating here because, you know, in the real game, in fact, he choose the A himself in the real game, right? But now, in this game, I've been here, the A is chosen by this guy, right? He doesn't choose himself. His goal is to guarantee that adversary does not notice any difference. Because if he notices any difference, then he will be thinking that I'm being cheated. Okay, he will abort the game. So the important part here is that challenger have to make sure that everything looks like in the real game. But why? Because in the real game, so in fact, challenger choose A uniformly random and compute Y, choosing X, right? And compute Y and send A and Y. But here is, in fact, it's the same distribution when he send A and Y to the adversary, because, you know, by assumption, the A that output that's sent by the challenger of the SS problem is uniformly random, because by definition of the problem, A is uniformly random, and the A in the one-way function also defined to be uniformly random. In fact, the distribution are the same. And and then he just given that the distribution of A in the real game and the simulated game is the same. Then he choose X and compute Y, so it's basically the same. So the adversary cannot notice any difference. And he won the bot game. And if he won the bot, then he have to follow his promise. He have to break the one-way function, right? Then, by assumption, adversary must return some x prime in 0, 1 to GM such that a times x prime equal to y mod q. Okay, so now the question is, what can the challenger do with this x prime? Okay, so in fact it's very, very close to this argument, where x and x1, x2 is just x and x prime here. Okay, so let x star be the difference between x and x prime. X is the vector chosen by the challenger, and x prime is the one returned by the adversary. Then we know that a times x prime equal to y times y equal to 0, right? Because a times x equal to y and a times x prime also equal to y. Then we know that x star here have dimension m and coefficient in the set -1, 0, and 1. And the norm of it is bounded by of m, right? Are we done? Are we done? Okay, so let's go back to the ground of C. So you have to find some x star, so that a x star equal to 0, right? So it's true here. And this one, x, the norm is bounded by square root of m. Are we done? No, of course, because x star must be non-zero. And we don't know whether it's 0 or not yet. We have to argue. Okay, we have to argue that x star is non-zero. Namely, x prime, the x prime returned by the adversary, is not the same with the x chosen by the challenger at the beginning with non-negligible probability. Okay, how to prove it? Okay, so we need the following lemma. For the given setting of parameter with m larger than log q plus n, and the lemma says that if x chosen uniformly at random in the set 0, 1 to the n, then with overwhelming probability there exists another x prime in the same domain such that a times x equal to a times x prime mod q. So so in fact, if for the given setting of parameter is satisfies this property, in fact, we work with a very, very big domain, and we compress the function to small range, okay? And we are saying that, the lemma say that if we choose some x uniformly at random in this domain, then with overwhelming probability, there is a collision. There exists another x prime such that choose x here, so there exists another x prime such that they map to the same thing. Okay, so that's what we are trying to prove. Okay, so the proof goes below. First, we can observe that there are at most q to the n minus 1 element x in the domain for which there is no x prime such that a times x equal to a times x prime of q. There exists at most q to the n minus 1 element x for which there is no collision. Why? Yeah, here this step is not easy to see. In fact, I myself also have a hard time verifying this. Okay, so we look at the set of on x here, such that there's no collision happen. Suppose that okay, so first we observe that this domain has size q to the n, right? Okay, so now suppose that we have this element that does not cause collision. So we map it to this one. So say it map to this one. And we look at the next one. Okay, and we map it to another one, does not cause collision. We keep doing this until the q minus 1, q to the n minus 1 step. Okay, it means that we fill every space here except one on the space. So I mean, the whole space q to the n, and if we can do this step q to the n minus 1. So what happened in the last step? In the last step, we choose another one, the q to the n element here, and we map it here. Now, that one must cause collision, because you know there's still many other elements here, and the next one you take the q to the n plus 1 element that you take here, it must cause collision because we already fill the whole space, right? So we can argue that based on this, that there is more q to the n minus 1 element that doesn't cause collision. And you know, because size here is much smaller compared to the size of the domain, then in fact, you know, the portion of this set that doesn't cause collision is much smaller to this one, to the whole set here. Okay, so this claim is verifiable. And then now we look at the probability that a randomly chosen x has a corresponding x prime such that a times x equal to a times x prime mod q. You know, it's now this probability is just like the probability that we choose x such that there's it will cause collision. And because you know the set here, the set that I draw here, is much smaller than the whole set, then probability that you choose a random uniformly random element that does not belong to this set is very big. Okay, so that essentially we can compute this probability. It must be at least 2 to the m minus q to the n plus 1. So it's the remaining element in the set, and divided by the size of the whole set. So we take the ratio. And we can show that it is very close to 1. This probability is very close to 1. In fact, it is at least 1 minus 2 to the minus n. And if n is big, in fact, this one is close to 0. So this one is overwhelming, very close to 1. So what we get from this lemma is that if x is uniformly random, then very likely that we will have another x prime that is that causes a collision. Okay, so let's go back to our game. When the adversary A returns x prime, then we're quite certain that x prime doesn't equal to x. But why is probability 1/2 here? At least 1/2. You know, when in the game here, in fact, the challenger, when he choose x, then the adversary had no knowledge about this x that he chose. When adversary return x prime, then we know that there are at least 2 of them that map to the same y. So the probability that you can guarantee that this x prime doesn't equal to the one that you choose is at least 1/2, right? Because we have 2 options, and the adversary, when we return one up, we have at least 2 options, and adversary just return one x prime, and the probabilities must be at least 1/2 that we can ensure that what adversary return is different from what we choose. Okay, then in this case, can guarantee with probability 1/2 that x prime is a valid 1/2 multiplied with the probability the adversary reckon the one-wayness of the function, and then now we have a solution to the SF problem with norm-bound square root of beta. And with respect to the matched A that we consider, And now we are done. Why? Because once we can argue this one, then the challenger here just return the X star to the challenger of the SF problem, say that, okay, I found a solution. And he can verify it's non-zero and it's small, just return this one and shown the SF problem. And now, because doing this is consider hard, then doing this also consider hard, meaning that the one function is one way. Okay? Any question here? Okay. Okay, so now let me briefly review another construction that basic, another simple construction that we can build from SIS. Is the collision resistant hash function. Okay, in fact, in the proof of one-way property of this function f, we essentially prove a stronger property, which is second pre-image resistant. Right? Like given the first image, it's very hard to find a second pre-image. In fact, that's what we prove. And in fact, that function f also satisfies another even stronger property, that is collision resistant. What does it say? It says that an adversary, after seeing a random function f in the family, cannot return x and s prime in the domain such that they are distinct and they map to the same image. Okay, so here in this game, you know, both of the x and s prime are chosen by the adversary. As long as he can find the two, then he can break the collision resistance. And you know, if you want to do the security proof for the given function family to be collision resistant is even easier, because by definition of the game, the adversary have to return x doesn't equal to x prime, right? We don't have to run through the probabilistic argument anymore. We know for sure that x star is non-zero, and we are done. So, and in fact, this function family is also collision resistant, and it can serve as a hash function. And you know, in practice, hash function can be used to protect data integrity. What we do is that we choose some x, we compute the hash value y, and we send y to the verifier, say. And as after some time, if we want to claim that, okay, so we have the pre-image, we just send the pre-image, and the verifier will verify, recompute the function, verify whether this one is y in fact the hash of x, and suppose that the function is collision resistant. In fact, you can this mechanism is secure because no one can find another pre-image for the same image. Another one consideration is when we don't work with one data item, but we work with a very large data set. Suppose say we have a set of n equal to 1024 data items, x1 to xn, and how can we hash and verify all of them? Okay, so one way to do that is we just hash one by one and do it. Okay, and we send all of the n image to the verifier, and he verify one of them one by one, each of them one by one. But when n increase, in fact, this kind of mechanism is not scalable, and it's incur linear complexity in the size of the data set, right? And a solution to do it, to make it more scalable, is to do what we call multiple hash trees, which is based on a hash function family that now is mapped to a domain consisting of two parts, d times d, and it mapped to d. It means that if you have 2k, an input of size 2k, one first part half the left is k bit, right k bits, and you map it into k bit. So it's just divided the input by 2 and get the output. Then we can build a hash tree. So this kind of mechanism was first proposed by Merkle in 1989, I guess. It's like this. Then you have the all of the data item here, and you can hash them. You can hash each of them step by step, recurse, and eventually you can compute the hash of everything here. And suppose that you have now the complete binary tree here, then you can map like 2 to the n, which is power up to say 1024 to just one item. And to verify it, in fact, you can do you can do it with complexity just logarithmic in the size of the data set. In fact, to verify, say that this element was hashed into y. So what you can give the verifier is just on of the node in the path from here, from this data item to y, and together with their siblings here, here, and here. And given on of the node, colorful node, then the verifier can recompute on of the hash based on this. And suppose that this hash function is collision resistant, then you can do the process within complexity proportional to the depth of the tree, right? And proportional to the depth of the tree means that logarithmic in the size of the tree, the number of leaves. So that's one way to enable data integrity with Merkle hash tree. It's very common method using nowadays. Okay, so in fact we can do with our modification of our lattice-based hash functions. Okay, so in fact we can just set the parameters so that we have two input and one output this way. In fact, we can set m equal to 2n log q. Then let's say k equal to n log q. Then in fact, this function usually it map m to n log q, right? So it maps 2k to k, 2k bits to k bits, and it satisfies the property needed for building Merkle hash tree. So that's one possible application of lattice-based hash function in data integrity. Okay, so now let me go to the second problem. It's LWE. Okay, so to define and understand LWE problem, so it's important to go through the concept of description of lattices. Okay, so in fact many works in lattice concerning complexity theory and cryptography use what we call a Gaussian-like distribution of lattices, and here we call it discrete Gaussians. Okay, so here what is the takeaway? So for every velocity m, the Gaussian distribution over the r to the m with parameter sigma is defined by this density function. Okay, so it's just. But now this is kind of the continuous Gaussian. You know, it has a bell shape, right? It concentrates around the center. Let lambda here be the lattice, integer lattice of dimension m. Then the discrete Gaussian distribution d lambda sigma is the m-dimensional Gaussian distribution with support restricted to lattice lambda. Okay. Let's try to draw something. Okay, so say we work with one-dimensional, and this is 0. Then normally the discrete Gaussian will have this kind of shape, right? So you see the probability and the sum of them is 1. But now we don't work with the continuous, but we work with discrete, say -1, 1, 2, and -2. So we only, the support only on the integers. Okay, it means that we only consider this probability. So the probability of that you take a sample from Gaussian discretion and it equal to -1 is like this. Okay, and the same here. Okay, so it's discrete one, and of course you have to scale them to make sure that the sum of this one over the lattice is 1. Okay. So it's how discrete Gaussian look like, and the property that is equal to something small is larger than the property that it is spread here. So when we go far away in two sides, so the property becomes small, and it will become extremely small when it goes too far. Yeah, in fact, we have a this kind of fact which is commonly used to tell inequality. So say that samples from discrete Gaussian with small parameter sigma are of small norm. Okay, so you see, for example, this K of dimension 1, we can see that if we take the sigma small, then the sample is very likely to be small. So in particular, if lambda is the integer lattices, then the property that x has the norm bounded by sigma multiplying with the square root of m for x sample from this discrete Gaussian is almost 1. So almost certainly, if we take a sample from discrete Gaussian, we can bound the norm. Okay, it's within the range, within sigma times square root of m with probability close to 1, overwhelming. So to make it simpler, we can view discrete Gaussian as something called beta bounded distribution, meaning that if we set beta equal to sigma times square root of m, then we can have that samples from this distribution have a norm bounded by beta with overwhelming probability. So we can just say that we can certain that this discrete Gaussian with appropriate chosen parameter is a beta bounded distribution. Okay, so now to define the FWD problem is we first describe what is called the LWE distribution. So we work with the following parameters: positive integers n and q, some beta bounded distribution chi over z. Okay, and normally we can think of n as the security parameter, q to be some modulatory poly n, and chi is a discrete Gaussian distribution with parameters sigma equal to alpha times q for some positive integer alpha, which is much smaller than 1. So the LWE distribution is like this. For a vector s in the q to the n, what we call a secret, the LWE distribution, what we denoted by a s chi over the q to the n times the q, is sampled by as follows. We first choose a vector a in the q to the n uniformly at random, and we choose some small noise from the distribution chi, and then we compute the inner product of a and s. So both of them are vector or in the q to the n. Then the inner product is an element of the q, right? We obtain inner product and we add some small noise e, and we output b. In fact, we output a and b together is a pair in the q. So a is the uniformly random vector that we choose in the q to the n, and b is an element of the q. So that is called how the LWE distribution is defined. In practice, we often work with M, which is a poly in N samples from the LWE distribution. So in matrix form, it's like this. So now we have an S here, the secret. First, we sample some A here, matrix A here. Oh, sorry, vector A here, and we compute the inner product, and we add some noise, which is more EI here. We output this BI. We do it M time. Okay. Then we can output the whole matrix A here together with all of the noisy inner product, would form, eventually form a vector B in GQ to GM. So you know it's quite similar to the SS problem, right? So in SS we have like A times X equal to 0, but this one also in the matrix vector form, you have the matrix, but now this matrix is faster and shorter. The parameters are quite different because for LWE we don't just want to build collision system hash function, digital signature, and so on, but we want to build encryption. And for yes. Okay, so it depends on some parameters alpha and q. So in practice, so you can think of it as we have a distribution which is bounded by beta. It means that it's a discrete distribution bounded by when we take a sample. So it is quite small, but it has a good entropy in the distribution, and we add it to the inner product. The support is an integer, so the output of the noise is some integer, a small integer. So basically you have a system. You have a matrix A here, and you multiply with your secret factor S. If you just output A transpose times S here, so it could be easy, right, to solve the system, because this one is you have a more equation more than enough equation to solve the system by Gaussian elimination, but you add some noise, so you make the system equation noisy. So basically this LWE problem involves solving a system of noisy modular equations over the Q. So the noise here you can think of it small and come from a good distribution with high mean entropy. And it's, here I oversimplify it by saying it is beta bounded, where for some small beta. Okay. Okay, so find two variants of the LWE problems. The first one is the search. So it's basically it say that for if you choose for S uniformly random and given matrix A and vector B, where B equal to A transpose times S plus E, following the LWE distribution, the problem X to phi S. Okay, solving this system, recover. This is the search version of the LWE. So okay, so we want to discuss this question. If there's no error, in fact, the problem will be super easy to solve. Because why we have more equations than variables, and we know that there is a solution. So of course, when we solve it using Gaussian elimination, it will give us the solution, the unique one. The noise is what it makes the problem hard. So you can guess that if we increase the noise level, then the problem will be harder. Okay. But if we increase too much, then also there's something wrong that I will discuss later. So it must be there must be some noise whose norm is under control. The LWE can be seen as an average K BDD problem. So for the BDD problem that we discussed earlier on certain family of QRE lattices, another family that I will define now. So you remember for the SS problem, it's related to the finding vector in a lattice called L bottom A, right? But now also for matrix A in the Q to the n times m, we can divide Q-array lattice, what we call LQA, which consists of on vector x of integer vector x of dimension m, such that they some vector s in the Q to the n, such that x is equal to A transpose times S. So it's basically consists of on of the integer vector x in the image, right? Of matrix A transpose. And why is it a lattice? Again, we can just follow the definition of lattice that we discrete subgroup of Z to ZM. We can verify that 0 belongs to this set, right? Because for s equal to 0, then A transpose times 0 equal to 0, and it's also a subgroup. It's easy to verify it, and it's discrete, so it's a lattice. And if to this form, this matrix vector form, then we can see that this vector B is very close to exactly one vector in this lattice, LQA, and the goal of the search problem is to find that vector. Okay, so now we have some intuition like this. We have a lattice, say, and we have a vector B here. We know that it's very close to exactly one lattice vector. So here in this case, okay, and the goal is to recover the closest vector to this B. Okay, so what happens if we increase the noise? We increase noise to, if it's too large, this distance will be increasing, right? At some point, the uniqueness property doesn't hold anymore. Okay, if we increase the radius here at some point, maybe it's too large like this, then you take this radius and in fact it covers more than one. So that's something that we try to avoid when we set parameter for FWE, because we want this function to be injective. Why? Because we want the uniqueness of S, and that is actually what makes FWE useful for encryption and beyond. Because unless for, in case of hash functions, we want to set the function so that it is surjective. But for encryption, so intuitively, we want to ensure that when we encrypt something, we should be able to decrypt to the plaintext that we started with. If we decrypt in two different things, then this system it just doesn't work. Right? We want to recover exactly the one that we started with. That's why we want this function to be injective, and we want to, given a ciphertext, we should be able to recover the plaintext. That's why we set parameter like this. And the noise is what makes the problem hard, but it should not be too large. Okay. To understand more about the mathematics behind, so I can refer you to real research paper about this. But in the scope of this short course, so I think I would try to make it simplified just to capture the main ideas. Okay. So in most cryptography system based on FWE, in fact, we indeed relied on what we call the decision version of the FWE problem. And the problem is as follows. Okay, so this one may be not very intuitively to understand, but let's go back one slide. Okay, so the decision problem is roughly as follows. Given A and B following the distribution, where S is uniformly random and B equal to A transpose times S plus E, the decision problem has to distinguish this pair, A and B, from a uniformly random pair. So now we have A uniformly random, but the problem say, okay, suppose that the decision problem is hard, then we can deduce that this B in this form also look exactly like a uniformly random element in ZQ to ZM. Although it's not truly uniform, but it's indistinguishable from uniform, even if it go in this way. Okay. So in the decision problem, so we give adversary A matrix A and B, and we ask him choose. Let me know this one come from which world? It's in a two world, truly uniform world when A is uniform, B is uniform, or the LWE world where A is uniform and B computed in the LWE way. If the adversary can choose the correct world with non-negligible probability, with probability non-negligibly bigger than 1/2, then it can solve this problem. Why 1/2 here? Because if the adversary doesn't have to do anything, he just to throw a coin and just give a solution. So in fact, he can succeed with probability 1/2, right? So now we have to exclude that part. We say that if adversary can distinguish with probability non-negligible, meaning that his success probability is not much bigger than 1/2, then he solved the problem. And our assumption is that the problem is high, meaning that no polynomial time adversary can do that. So search and decision, in fact, they are equivalent. And we can see it intuitively like decision is not as high, search is at least as high as decision. It's quite clear because given A and B, if you can recover S, you know that this is not random. So you can solve the decision. And what the contribution of Regum is that he showed that the invert direction. He showed that decision is also at least as high as search. So if you can solve decision, then you can also solve search. Okay, so theorem of Regum is follows. For any M, any modulus Q, any distribution chi of the form which is discrete over the Z here, our lattice Z, integer lattice, and with parameter sigma equal to alpha Q, where alpha Q is not too small. Okay, it's at least 2 times square root of n. So it's important because if the noise is too small, then the problem can be solved efficiently. So we want the noise to be moderately large. Then solving search and decision LWE is at least as high as solving gap SVP or SIVP on any n-dimensional lattice on the quantum computer. For some parameter of gap approximation factor gamma depend on n and that proportional with n divided by alpha. Okay, so as I mentioned previously, there is a quantum word here. It means that this reduction only guarantees that if you can solve LWE, then you can solve. You can also solve lattice problem on a quantum computer. So this is a strong assumption, right? And it's not, in terms of reduction, it's not a good reduction. Not too good, but still usable, because currently we don't know any quantum algorithm to solve lattice problem. But maybe it's easier to find a quantum algorithm to solve lattice problem than to find a classical algorithm to do the same thing. Okay, so we can try to check the hardness of every based on this theorem. First of all, if n increase, then how the problem will behave? If n increase, then in fact you are dealing with lattice of higher dimension, then problem will be harder. Okay. How about M increase? Then in fact you see, look at the reduction here. In fact it doesn't play any important role. As long as M is polynomial, is fine. So it doesn't really affect on the hardness of the problem. But alpha increase, then you see that n divided by alpha will decrease, right? And then gamma will decrease, mean that problem will become harder. So alpha increase, the noise increase, problem become harder. But to make it usable, as I mentioned, we have to make sure that it's not too large. And Q increase, so it's a good question. So currently we don't know yet, but it seems that at Q increase, the problem also become harder. But it's still currently still ongoing discussion about this. Okay, let me also mention some attempt to remove the word quantum here in the reduction. So for now, 2 attempts have been made. Okay, so the original work Regum was given in the conference of Stock 2005. It's one of the main top conferences in theoretical computer science. And 4 years later, in Stock, Euro 9, Picard tried to make the first attempt to remove this quantum work. It means that he showed that solving LRB as solving the lattice problem on a classical computer. But his reduction only worked for very, very large Q, which is exponential in n. So it gives I mean, if Q is too large, then describing elements of the Q will take a lot of bits, right? Then the problem becomes less efficient when it's used to build lattice-based crypto. And another attempt was made by Perpustakaan et al. In Stock 13. Okay, and but it only works for smaller n. In fact, it says that if you solve LRB with this dimension n, then you can solve lattice problem in a smaller dimension. So it also there's some drawback in the reduction, even though it is classical. Another result was done in Crypto 2009 is that it says that initially the secret of LRB S is chosen uniformly at random from the set Q to the n, right? But the authors of this work also show that the problem is remain the same, at least as high as the original version if S is chosen from the same, if the same distribution with the errors. I mean the coefficient of S and the coefficient are chosen also from the errors. I mean that the problem remains high if S is small and follow the error distributions. And also some recent work, because you know when dealing with Gaussian is quite complicated and very hard to implement as well. So there's some attempt to obtain harness results for LWE, which slightly different distribution. For example, LWE now is known to remain hard if E sample from some Gaussian distribution like uniform. But with some, but the result only hold for some bounded number of samples. It's not any polynomial. So number of samples have to be determined in advance. Okay. Let me talk about the non-cryptographic application of LWE. In fact, LWE is much more powerful than SAS. We can build much more interesting crypto system based on LWE than what we can do from SAS. So Regum and others results saying that LWE have security guarantee from lattice problem, and other people show that cryptography can be built on the search and decision version of LWE. Some example as follows. in fact, it's much richer than SAS. You can do one-way function and pseudo-random generators, public key encryption, key exchange, chem, pseudo-random function, some protocol called oblivious transfers, many advanced form of encryptions like identity-based, attribute-based, functional encryption, and fully homomorphic encryption, and much more. Okay, so one quite easy to see application is for one-way function and pseudo-random generator. So we consider the function GA. So say we have on input matrix A in GQ to the n times m. We consider the function GA that map two inputs. One is GQ to the n, and the other one is minus beta to the m. So it is a set of integer vector whose infinity norm is bounded by beta. And we want to make this function, and it maps to the q to the m, and we want to make this function injective. We want that the size of the whole domain here is smaller than the size of the range. So it's in contrast to the SAS, we want the domain is much bigger than the range. Now we want this function to be injective, so we set the domain is smaller than the range. Otherwise, the function is not injective. So given matrix A, and for S, uniformly random is q to the n, and error vector, noise vector E of dimension m. So the function of S and E with matrix A is defined just to be the LWE relation. A tends both times S plus E. And we can easily directly show that this function is one way, right? Suppose that the search problem is hard, then this function is one way. Because what the subproblem acts is to given this GASE which convert vector B, we output A and B to the adversary output a solution, invert the function. But in fact, by doing this, he also essentially shown the third problem of LWE. Okay, so second application, also immediate application is pseudo-random generator. So in pseudo-random generator, we have some SIP S here, and we want to generate some randomness, right? Which is computationally indistinguishable from uniform. So if we start with n log q uniformly random bit here, and we want to generate m log q bits that look like uniform bits. That's the goal of the pseudo-random generator. We want to start with a smaller amount of entropy. We want to generate more random bits. Okay, and if we define the pseudo-random generator this way, then in fact it is a secure one. We can certain that this function is computationally indistinguishable from uniform if the decision version of the LWE problem is hard, right? Because it's just very straightforward. Decision act to distinguish this guy from uniform. If we can distinguish, then you don't this one and uniform, and then it's shown the decision version of the LWE. Okay. So now we have like roughly 15 minutes left. So let me go skip this subsession and go to PKC encryption from the This commitment from SE is an easier notion, and maybe I will provide. You can check the slide later, which will be available for you after the course. Okay, so would it be okay for you if I go past 12:30 a little bit, because I want to emphasize on the definition of how to define a secure public encryption system. Okay? Okay, thank you. Okay, so as before, when we want to define some crypto system and we want to prove security, the first step is to define rigorously what does it mean for this to be secure. So a public key, first we define what is a public key encryption system, right? It is a triple algorithm: key generation, encryption, and decryption, and with some message-based M. And all of them are polynomial time algorithm, for sure, obviously. So the key generation algorithm take input the security parameter, and it output a public key, a pair of public key, and secret key. The encryption algorithm take as input the public key together with the message M in the space. Output a ciphertext C. Decryption algorithm take input the secret key and the ciphertext and return M. Okay, so this is just a standard definition of public key, where you use the public key for encryption and you use the secret key for decryption. So for any public key encryption system, we have to guarantee two things. First, it must be correct. Second, it must satisfy some security property. So what does it mean for a public key encryption system to be correct? So for correctness, we want that if we encrypt M, then when we decrypt, we must receive the same M, right? That is the basic property. If we receive the other M, then it's not useful. So more formally, for any pair public key secret key PKSK outputted by the key generation algorithm and any message M, we have to ensure that the probability that we decrypt using SK for ciphertext encrypted with PK and M, and we receive M, and we want the probability is very close to 1. In fact, for perfect system, we want this one to be exactly 1, but for some system like LWEs, and maybe because we work with probabilistic algorithms, maybe something go wrong during the process, we go with a bad randomness, for example. So maybe there's some very small decryption error. Okay, so here we relax the definition to allow some negligible probability of error. But anyway, so it's negligible in practice means that it's almost 0. So it means that we want this one to be almost perfect. Okay, so the very basic and conventional notion of security for public encryption is called indistinguishability of ciphertext under chosen plaintext attack. So it is basically what was introduced by Goldwasser and Mikali in their seminal work that gives them the Theorem of Regum. So they captured the notion that given a ciphertext, no one can learn any piece of information about the plaintext. Okay, so this notion is formally called as this one, and or in short in CPA, indistinguishability under chosen plaintext attack CPA. Okay, so this defined follow. As for the one-way functions, when we work with this one, so we have to consider a game between a challenger and the adversary. So the challenger just run the key generation and obtain a pair of public key, secret key, and as you expect, so the challenger will give the public key to adversary, right? In fact, it tries to model the real scenario in real life. When you set up a system, in fact, you generate a key pair and you publish your public key to your website. Of course, you have to keep secret key for yourself, okay? And now this is the interesting part. So A adversary will send back two messages. Okay, it's M0 and M1, two messages. They are distinct. Okay. And now, okay, so now it captured the part that adversary can choose the plain. So in short, we want to see to capture the following property. Adversary choose two plain tests. We encrypt one of them. We give the resulting ciphertext to the adversary, and we let adversary choose. Okay, let me know. This is the ciphertext of which message that you have chosen, M0 or M1. If the adversary can choose this one, can guess with non-negligible advantage, then he wins the game. So by a hybrid argument, mean that all of the ciphertexts under of any message will look almost the same. If they look almost the same, it means that you can not learn any information about this. Okay, so but here we have to model this. That's the intuition. We don't, but we have to model this by some kind of bit here. So the challenger choose one uniformly random bit. Challenger just throw a coin, get a bit B, and encrypt MB. Mean that either M0 or M1, right? And get a ciphertext C star and send C star to the adversary. Adversary, so now he have to return a bit B prime, which is a guess. And it wins the game. His guess is the same as the bit we choose. So given the C star here, he say, okay, I guess this must be a ciphertext of M0. And he output 0, B prime equal to 0. And if B, the B that the challenger choose, happen to be the 0s, and he wins. And we repeat it many times. He has probability of guessing is non-negligibly larger than 1/2, then he wins the game. Okay. So more formally, we can define the advantage of adversary in this game as a function of the security parameter n, called advent A of n, which is the probability that he can get that B prime equal to B and minus 1/2 here. Okay. And we can take this one like the absolute value of this one, just to guarantee that the advantage is non-negative. And then when we have defined the advantage, we can formally state what does it mean for a system to be in CPA secure. The scheme is called in CPA secure if for any polynomial time adversary A, the advantage of this adversary is at most negligible in the security parameter. Okay, so now polynomial time adversary can win the defined game with non-negligible probability. Is it clear to you? So adversary can try, because you know, in the real world, in fact, the adversary is the one who encrypts, right? So in fact, he can choose the message, choose the plaintext himself. But the thing is that if you do that if you by yourself, and the adversary maybe chosen can choose M0 and M1, he cannot guess this one. So in fact, it captures the intuition that the ciphertext should not reveal any information about the plaintext. Okay, so here a very simple question. Can a deterministic encryption system be in CPA secure? Just to clarify this definition a little bit. Can a deterministic encryption system be in CPA secure? So I mean the encryption algorithm doesn't take any randomness. Can it be secure? Who think is yes? Who think is no? So everyone thinks is no. So in fact, all of you are correct. Okay, so if this system is deterministic, it means that given M0, you can only obtain one C0. And given M1, you can obtain only one C1. In fact, it's not secure because the adversary can trivially win this game because he can compute the encryption by himself, right? It's deterministic. Just compute this one, and whenever you return him C star, so it's fine. Just he can guess with 100% probability. That is the C0 or C1. Okay, so it means that if you want in CPA security, you have to make sure that your encryption algorithm is probabilistic. In fact, this is the one of the main contribution of Gowers and Mikali. So that okay, forget about deterministic encryption. It cannot be secure under our definition. Okay, that's very important. So you know, in the World War II, so some of the military powers was make a mistake in this one because there's no definition of in CPA security 60 years ago, 70 years ago. Then all of the encryption algorithm was deterministic, and many of them were broken by the enemies. Okay, so the lesson learned is that we have to work with probabilistic encryption. Okay, so I will describe the first public key encryption system from LWEs, which were also proposed by Regev in his seminal work that introduced the LWE problem. I will not, unfortunately, have time to prove security of this one, but I will give some informal argument that why it can be secure under LWE, and you can check my slides after the course about the detail. Okay. So, Regev's encryption system work as follows. We take some Q, modular Q, some dimension, and some beta, some bound beta, and let chi be the beta bounded discrete Gaussian distribution. And here is the version of the scheme that works with message base 0 and 1. In fact, you encrypt only one bit. So the key generation is as follows. So basically, you output an instance of algebraic problem. You choose a uniformly random matrix A and uniformly random S and sample some error vector and just output AB, where B is in the algebraic way equal to A transpose times S plus E, and you keep S as your secret. The algebraic secret is your secret key. So it's very intuitive from LWE. So given this one, you will hope two things, right? You will hope that given A and B, if the search LWE problem is hard, then adversary cannot compute your S, right? And the second thing is that given A and B, you hope that if the decision LWE problem is hard, adversary cannot distinguish this pair from uniform. In fact, the B here, from the adversary's view, is like a uniformly random vector in the Q to the M. Okay, so if the LWE problem is hard, so we can guarantee that the public key is secure. Okay, so the encryptions work like this. So on input, the public key and a message, which is a bit M, a uniformly random R in 0, 1 to the M, and compute two things. First is a vector U equal to matrix A multiplying with this vector R, the randomness. You know, the encryption must be probabilistic. It means that in the encryption process, you have to introduce some kind of randomness. So this one is A times R, where R is the random bit that you choose. And the second part is B transpose times R is the inner product of B transpose and vector R plus M times Q over 2. Write it down. And this C is a pair of a vector and a scalar. Okay. So for decryption, so the input could be your secret key, right, and a ciphertext here. And what you do is you compute the inner product of S transpose and U, and you take V, subtract it in the product, and you obtain some M prime in GQ. And now you do the check. If M prime is closer to 0, then to Q over 2, mod Q, then you output 0. Otherwise, you output 1. So it's like this. When after you do the V minus S transpose U, so you obtain some M prime. So say this one is Q over 2, this one is 0, this one is Q. So if your M prime is around this one, closer to this Q over 2, then you return decryption algorithm return 1. On the other hand, if it is close to 0, so it may be here or here, right? Because Q mod Q is 0 here, just period. Then you output 0. Okay. So you can think about the scale by Q over 2 is like the way you encode the message, so that you can do some encoding before encryption, and you do some decoding after decryption. Okay, so here we have the theorem about its correctness. So the theorem says that the scheme is correct with overwhelming probabilities. Means that if you encrypt M, then you will obtain the same M with probability negligibly close to 1. In this, we can check as follows. Recall that M prime is V minus S transpose times U, right? And now remember that V is which form? V in fact is equal to B transpose times R plus M times Q over 2, right? We just replace it here. And minus S transpose, and you know it's U. U is the first part of the ciphertext. It's equal to A times R. We just replace. Okay, because we are proving correctness, so we assume that the ciphertext had this form, right? So we just replace everything, and now what happened here is that we know that B, the public key, part of the public key has the form A transpose times S plus E, right? So we just replace. So B transpose will have the form S transpose times A plus E transpose. We just replace B transpose to by this one. And now this step just doing that, and now you see this factor S transpose times A times R appear here, so it's cancel out. Okay. So what we remain in M prime would be the inner product of E transpose times R, which are N M times Q over 2. Now the observation is that recall that we choose R to be uniform in the set 0, 1 to M. It means that all of the coefficient of R is 0 and 1. It's very small. And E also have entries bounded by beta, right? So when you take the inner product, in fact, the inner product will be a small element of the Q. If we set the parameter, say, you set Q sufficiently large such that E transpose, so that its inner product is much smaller than Q over 4. Then, in fact, we will have this situation because we have a M times Q over 2 plus some small noise. Okay, as long as the noise level doesn't exceed Q over 4, in fact you have a unique decoding here, right? If it's too big, in fact, suppose that the two circles have some intersection. In fact, we are in trouble because we don't know where to decode. But as long as we set the parameter such that the inner product of E transpose and R is smaller than Q over 4, then we can successfully recover the M. So here you can see why we have to encode it. We have to scale with 0 and 1 to make it very far from each other, and then we have the radius in between. But why is it only probabilistic? Because you know, this R we know the norm, but for E here, because it's sample from distribution. So based on the tail inequality, we can guarantee that the coefficient of E is very small. But I mean, in the worst case, it may be large. Just one of them is large, for example. Then decryption. Then you know that the inner product here will be larger than Q over 4. In that case, the decryption is not correct. So what we can guarantee based on the tail inequality is that decryption will succeed with overwhelming probability. Okay. So now let me state the security of the system. It says that if the decision LWE's problem is hard, then the given scheme satisfies in CPA security. Okay, so it's gone through two steps. Okay, so informally, like this. So as I previously argued, the public key has this form A and B, where B follow the LWE shape, right? Follow the LWE distribution. So by the hardness of decision LWEs, we know that A and B, this pair is computationally close to a uniformly random pair. Suppose that decision problem is LWE is hard, then we can deduce this fact. And now you look at the ciphertext. In fact, you know, U equal to A times R. So here I plus 0 is still the same. And V equal to B transpose times R plus the message. You see, in the CPA game, when we return this one to the adversary, then we can argue that what we return to him is in fact indistinguishable from uniform. Why? Because suppose that this decision LWE problem is hard, then we can change it A, B transpose from LWE distribution to uniform distribution without being noticed by the adversary. So now at this second step, we can assume that A and B transpose is totally uniform. So now there is another lemma called the leftover hash lemma. It says that, okay, so you can view this one as a hash function, where the public keys, the key for the hash is A concat would be transpose, and what you have is R. So there is a lemma saying that if your pre-image is sampled from a distribution with sufficiently large mean entropy, and this function, the hash function is universal. Okay, it has some property. Then the output E of the image of the hash would be statistically close to uniform. So it allows you to extract some randomness. If you start with some good source of randomness and you compress them, then you can extract perfect randomness. So that's essentially what happened here. Using this leftover hash lemma without any computational or some statistical argument, we can argue that this part is statistically close to uniform. So basically, even the adversary has unlimited power. It cannot distinguish one from uniform. And now, if this one is uniform and you plus something, you add something, the distribution is still uniform, right? And uniform plus something is uniform. So the ciphertext is even two steps. So the ciphertext, in fact, is computationally close to uniform. the challenge subtext C that you C star that you return to the adversary. And because it is computationally indistinguishable from uniform, then the adversary cannot guess with non-negligible advantage because it looks like a uniformly element in the subtext space. So the adversary, suppose that FW is adversary cannot win the game. Okay, so the formal security proof is a little bit more involved, and unfortunately we don't have a time to cover this. I hope I have 1 more hours, but I think we are all hungry. Okay, so in fact, I in the slide also put a related version of Regep system which called the dual Regep, which was proposed by Genchi, Picard, and Vakunutan in Stock 3 years after that. This system also has some nice properties similar to Regep, but it has application in more advanced encryption system like IBE, identity-based encryption. Okay, I think that's all that I want to tell you in these 2 lectures. Thank you very much.
Okay, thank you, Dr. Khoa Nguyen, for the lecture. And please stay on the stage. There's a souvenir from the committee. May I invite Dr. Diah Junia Exi Palupi to come to the stage and hand over the souvenir to the speaker. Give an applause. Okay, this is the end of the second session, and the next agenda is lunch.